Welcome to the final video in Unit 3A. It has been a long journey and I'm glad you made it to the end. We are now going to talk about Earth's revolution and some of the other motions that we have learned in modern times we are undergoing. We talked about rotation in the last video, which is Earth's motion of spinning on an axis. I also introduced you to the term of revolution, which is the same as orbiting another object. You probably don't realize that we're orbiting the sun at a pretty amazing speed, 66,000 miles per hour. Now, why don't we feel that? I'm going to talk about some other motions as well today. And these motions are very fast, but I don't feel it. I'm not moving anywhere, as far as I know. It's because we're moving at a constant speed. We're not accelerating or decelerating. When you take off in an airplane or a car, you get pushed against the back of your seat because the vehicle is accelerating. You notice the change. But once you're at a constant speed, like if you're cruising on the highway or cruising in an airplane, you wouldn't know that you were driving or flying unless you looked out the window. And that's because you're at a constant speed. So we don't notice that we're going at 66,000 miles an hour around the sun because we've been doing it our whole lives. Now, if the Earth suddenly stopped or changed, suddenly slowed down or sped up, that would be catastrophic. I've described before how the Earth and other planets have elliptical orbits around the sun. I'm not going to ask you about these terms, but just in case you're curious, there are names for when our position is closest to the sun. Perihelion, peri means close and helion means sun, and aphelion for our farthest position. Ap means away. Interestingly, we're closest to the sun in January, and we're going to be talking about seasons in a few weeks, and so that's a little hint about how the seasons might not be related to how close we are to the sun. In any case, I do want you to know the second thing on this screen, which is the plane of the ecliptic. And I did mention this in the Lab 3 video instructions. The ecliptic is this imaginary flat plane that is swept out by Earth's orbit. And here's a picture showing that. This green area is the ecliptic. Here's the sun, and here's the Earth in various positions throughout the year. And so that plane that is defined by our position is called the ecliptic. What's shown down here, another thing related to seasons, is that the plane of the ecliptic, again shown in green, is not parallel to the plane of our equator, which is shown in blue. And in fact, they're 23.5 degrees away from each other. And this is why we have seasons. So again, we'll come back to the ecliptic. When students start learning about astronomy, they think they're going to learn about constellations. And in fact, constellations just are random orientations of stars that people have seen and decided make some sort of shape, and sometimes there are legends and stories about them. This one here on the left is Orion the Hunter, and in fact other cultures have called it different things. You might recognize the hunter's shoulders, belt, sword, legs, and shield, and arm with the sword. This is a pretty good shot. I don't know if Los Angeles has the greatest viewing to see all those stars. But in reality, those stars are nowhere near each other. So here's another view of those stars, a little bit brighter so you can see them better. And I'm going to show you a side view of how far these stars really are from each other. So this is from 0 to 1,600 light years. A light year is a very, very long distance. And these various stars are really very far from each other. So constellations don't really have any scientific meaning. If we could be Star Trek and go out to other places, Orion wouldn't be there anymore because we'd be looking at the stars from a different orientation. Now, that said, all of us have been assigned a zodiac sign when we were born, right? And so I want to say a little bit about the zodiac constellations. So here, once again, is the ecliptic with the Earth and some of the other planets and the sun. And the zodiac constellations are the ones that are pretty low around the horizon. Up here at the north celestial pole would be Polaris, the North Star. In this particular figure, the sun is in Virgo. So if you were born on Earth when the Earth and the sun are in this relative position, you would not be able to see Virgo because the sun would be in Virgo. And I think that's from mid-September to mid-October. So your daytime sky is going to be in this direction. Your nighttime sky is going to be in this direction. And so you would be able to see these at night. 6 months later, when the Earth is over here, you would be able to see Virgo quite nicely. And these constellations over here would be out of view because you'd be looking towards the sun. So that's why the constellations are not seen year long, because they're low in the sky and sometimes the sun is in the way. Constellations that are near the celestial North Pole, like the Big Dipper and the Little Dipper, we can see pretty much year round. Okay, so moving on to other types of Earth motions besides rotation and revolution. The Earth also precesses like a toy, like a top. So I don't know how many of you ever played with tops because you have the internet and electronics, but an example of a child's top is shown here. You pull a string and it spins, and then slowly it precesses in a circle and then it falls down. A gyroscope does a similar thing. Well, it turns out the Earth does this as well. Right now, the Earth's spin axis is pointed to the North Star. But in fact, the Earth has this wobble where it precesses very, very slowly, and the direction of where the spin axis points changes. In fact, the cycle is quite long. It's a 26,000 year cycle. So today, we are pointed at Polaris. As time goes on, our spin axis is going to point at stars in the constellation Cepheus, and then near Cygnus the Swan. And in 14,000 AD, we'll be pointing near a star called Vega. And so that's what's shown up here. And eventually we'll precess back to where spin axis is aimed at Polaris in 26,000 years. So that's a motion that we have figured out in recent times. Another type of motion is that our entire solar system is moving with respect to other stars. So this is a cartoon of our galaxy, the Milky Way, and our solar system might be located around here. And our entire solar system is moving in the direction of the star Vega. Now, it's just a coincidence that it's Vega again. Finally, all the stars in the Milky Way are revolving around the center of the Milky Way, like this. It takes us about 200 million years to go around once. So the last time we were in the position we are here, the dinosaurs were roaming the world. It was about the beginning of the Jurassic. How fast are we going around the galaxy? It's difficult to figure out these speeds, but it's been estimated at about 500,000 miles per hour. Or, kind of appreciate this one, we are moving with our galaxy at about 1 AU every 8 days. Now remember, an AU is the average distance between the Earth and the Sun, which is 93 million miles. So every 8 days, our entire solar system moves the distance between the Earth and the Sun. Incredibly fast. And we don't feel it because it's a constant speed. Finally, our galaxy is moving relative to other galaxies. We are one of a group of galaxies called the local group, and we'll talk more about this later on in a week or two. Our galaxy is part of a galactic cluster, and it's shown here with the Milky Way in the middle and other galaxies listed. And this is a 1 million light year radius, this first blue circle, and then 3 and 5. So this is a 5 million light year radius. And we are moving relative to these other galaxies, somewhere on the order of 1,350,000 miles per hour. Wow, that's crazy. So I just want to summarize this journey that we've taken during Unit 3A, which started with the ancient Greeks who thought the Earth was fixed, non-moving, and everything moved around it. And we found out In fact, that not only are we rotating and revolving, but we're hurtling through space and the universe at incredible speeds. Coming up next is Unit 3B, a focus on our solar system.